Hi, everyone. I'm Aditi Pandit. I am a software engineer at IBM working on What's Next data. And I am going to talk about table value functions in PrestoC mode, the Presto native engine. So, in the talk, I'll quickly go over what table functions are and give some motivating examples. Then the next part would be about the SQL syntax for table value functions. Then talk about the TVF APIs, and then go a bunch of starter TVFs that we wrote that illustrate the usage of the APIs. So what are table value functions? Table value functions return a table. And so they're another family. You can think about them as a family of functions like scalar or aggregate or window functions, but the table functions return table. They are used in the SQL from clause, and they compose as a table with the rest of the queries. Table functions are very popular extensibility in SQL. Polymorphic table functions are part of the 2016 SQL standard. These functions are available in all major query processing engines, Snowflake, BigQuery, Trino, Teradata, all have them, and they are broadly used for very diverse things, advanced statistical and ML functions, pattern recognition, model training, and federation uses like a connector. So I'll kind of go over some of these with examples. So I picked up like a bunch of popular TVFs, and these are from different SQL engines, so there are subtle differences in the syntax, but I basically want to motivate why table functions are there. So this is like a fairly sophisticated analytical table function, probably the most complex analytical function I've seen. It's called NPath from Teradata, so used for funnel analysis, fraud detection. But the general idea is that you have a click stream, so just a series of rows which are like log events. So what the user intends to do is that you have the click stream, which is, so on is kind of like a table. So the input table is a click stream partitioned by user ID, order by events. And what they want to do is so they're going to look at this page column in the click stream, and they're going to map the value in the page column to symbols. So if you're on the home page, it's A. If you're on checkout, it's B. If you're on purchase, it's C. And what the function is going to do is going to identify a pattern of A followed by any symbol, followed by B, followed by any symbol, followed by C. So a user has come in, visited the homepage, browsed a bunch of items, done checkouts, and is going to do a purchase at some point in time. So it's going to recognize this in the log stream of that user ordered by time. And what are the results? The results, a bunch of things. So the user ID, when such a sequence was detected, so valid user came in, checked out, and purchased. The number of times they were on the homepage, so the number of items they actually looked at, the first time they entered, and the last time, so the purchase time that they have. So this is all that they want to do in one function. And what's amazing is that this function is very flexible. So you can take any table partitioned by user ID. The signature is not really telling you what exactly are the columns that are going to be returned by this function. And depending on how you have invoked the function with all these different parameters, you decide in a very polymorphic way what are going to be the result columns at query time. So this is, if I had to do this just with SQL without table functions, it would be crazy number of joins, just never complete on a big table. So this is pretty impressive. Another common use, this is something I picked from BigQuery Snowflake. So they have all these table functions for invoking machine learning models in a SQL query. So again, the input is TS value from metrics, a metrics table, and they're looking at timestamps between today and 7 days. And this function is going to it takes this model, is going to build like the anomaly model, and based on a certain threshold that the user is sending in this, is going to identify all the outliers and return those rows back to the user. So this is also like very commonly used in infrastructure monitoring, fraud signal detection. And this is something from Trino. So Trino has this JSON extraction function, and you can pretty much say from a payload, extract all these columns with these different paths. And so depending on whatever is your column and whatever you have defined as these column paths, the query returns different columns different times. So this query is also interesting because it didn't really specify the input table for JSON table function, but it is a join with orders. And so this is like an implicit lateral style where the orders is actually a table argument to the JSON table function. And the payload is like some column in the orders table. So these are like the sophisticated things folks want to do with table functions. And we had a bunch of advanced use cases in what's next data. And so that's why we went ahead with building this. So I hope that motivates why table functions are fun and interesting. And yeah, so now I'll go more into the details of how they appear in SQL queries, what are the components of a table function, and kind of go over the API that we built in Velox for it. So TVFs, in terms of SQL, TVFs can appear as tables in SQL statements. So we kind of stayed very close to what Trino has, so that like users can easily port functions over. Table denotes a table function. In this case, we have mock, system, different arguments. So this just tries to illustrate all the different kind of arguments you can have to a table function. So like table function can take tables, it can take scalars, it can take descriptors, which kind of denote columns. So in this case, there are 3 table inputs. And like window functions, you can partition an order by a table to invoke like the table function logic on a partition at a time. So in the parameters here, you see that input 1 is partitioned and ordered, input 3 is only partitioned, and input 2 is not partitioned or ordered. So, and then there is this co-partition clause which says that T1 and T3 are co-partitioned, which kind of means that we want the same values of C1 and C3 to appear together in a partition. So how is this function planned? So you're going to have the 3 tables, and 2 tables are going to be partitioned and ordered like window functions. And then there's going to be a join to put the rows with the same values of C1, C3 together, and all values of input 2 table. And so each of those partitions is going to be run like a window partition and going to execute the user logic. Some SQL concepts about TVFs. TVFs are polymorphic. So like mentioned, the function signature doesn't tell you what are the types of the tables. And so like they can be invoked with any table. And you know what are the columns, output columns of the result of the table function at query time. So like just taking this simple function, so we have this function called exclude columns, which is basically just doing like select star except, but it takes a table and it says that just remove these columns from the table. So like in the 2 invocations, right, one invocation says remove columns, clock and comment, the other one says just remove comment, and these 2 queries, although they're on the same table and the same function, they're actually going to return different columns back. So that's like the polymorphism of table functions. So table arguments, they can be tables, descriptors, scalars. So tables are just tables. They can have partition by, order by, and co-partition, like I explained before. And there's also a subtle nuance whether to prune or keep an empty. So this kind of tells the framework that even if you have an empty table, invoke the table function or not. Scalar arguments are just like literals. And descriptor arguments is, descriptor is a spec to tell that, to identify columns and types. And that is also used by the, that can be used by the function to pick out some particular column in the table function. Arguments can be passed by name or passed by position. So like every argument can have a name, and you can, your table function invocation can mix and match the order of the arguments because of the name or positional passing. So yeah, so how do table functions execute? So because table functions are polymorphic, they have signatures, but the signature tells you that just that my table function takes 3 arguments, and those arguments are table, but it doesn't list out what are the columns of that table. So the user has to first write the signatures and register their functions in a registry, like what is done for scalar and aggregate functions. So when a SQL query comes in, depending on so when the parser sees the usage of table and sees the function name after that, it tries to match it up in the registry and gets like the signature of the table function. From that, it knows which arguments are tables, which arguments are literals, or which arguments are descriptors. It maps them correctly, and then it also participates in the statement analysis. So during statement analysis, which is basically binding every parse node in your SQL query to the relation, so to kind of say that every, like parse node is actually going to give me this table. So so table functions also have to implement an analyze API. And this analysis API, the user provides all the parameters. So if you have table functions, it gives what are the columns of that table function, and during analysis, the function can validate the table arguments, do some calculations, and return back to the coordinator that this is the schema of the output table of the function. And post-analysis, this table function node is compiled into the query plan, and during execution, table functions are executed like other operators in the velox plan. Because table functions can be invoked with input tables or without any tables at all, the operators could be like leaf operators, or they could appear within a pipeline. So there are 2 different APIs that a user can use for this kind of handling. So one is called a data processor, one is called a split processor, depending on whether it appears as a leaf or as an intermediate operator in the pipeline. So yeah, so to kind of visually describe, your SQL query comes in, hits the Presto parser. The Presto parser looks up the registry, looks up the arguments, tries to map the arguments. The next, so it maps everything and creates like a table function parse node. This is sent to the statement analyzer, which is actually kind of mapping every parse node into like the relation or the columns of every node. And that statement analysis also calls the analyze API of the table function. That tells the statement analyzer what is going to be the output schema of the function. The planner then like plans a table function as a join or window functions, depending on the variety of arguments that it has. There's also one fast part to just replace a table function with a table scan of a connector. So that is also one fast part that we added because many folks just tend to do that. And once the query is planned, it becomes ready for execution. And during execution, the author provides a data processor process function or a split process function that operates on every partition or every split of the data. So yeah, so that means that there are a bundle of APIs. So everything is very velox style. So you have function registration. The user has to write a register table function, which provides a name, the arguments of the function, a return spec, meaning that whether it's a generic table or if you know in advance what the schema is going to be, you can also fix the schema and give it at registration time. An analyzer function, which will be called during statement analysis, the data processor factory. So you can have a data processor or a split processor. And if you are going to process the table function as a leaf, it will have a split generator because you need to distribute the processing of your table function into units that can be executed on independently. So yeah, so in terms of like the table arguments, we have an argument spec. So the argument spec tells you what's the name of the argument, whether it's required or not, what's the default value. And then because there are so many different kind of arguments, you have a scalar argument spec, a descriptor argument spec. So scalar argument tells you the type of the argument because it's a literal. The descriptor tells you the name and the types of the columns. And then a table argument specifies a table. It tells you whether this has row or partition semantics, whether to retain it or skip it if it's empty. And it also you can also specify whether it's fully passed through, because in many cases you actually want to pass through the entire table and just compute one additional column or something. And so the user has to write an analysis API, and the analysis returns to the framework what is going to be the output schema of this table function. You can also return a required columns map, which basically tells you that although you have these input tables with so many columns, I'm actually only interested in these columns in my table function for the processing. So this helps the optimizer with like projection pruning. And if you know the output schema of your table function already, it's fixed, you can return a return type. Oh no, actually return type is like the output schema. And the table function handle is like if you have pre-computing some metadata which you have computed at optimization time, but you want to give it to every worker during execution, you can put that in what is called a table function handle, which will be just sent to the runtime. So in terms of, that is all the analysis, and then the execution, you either work on a partition at a time, so you either write a data processor, which has an apply function, so you get a vector of input rows, and you return table function result, which is a status, which tells you either that it's consumed all the input or it is going to do one more round of processing. And you also return the output rows that you've generated. So there's kind of no relation, there doesn't need to be a kind of relationship between the input row and the output row. So any set of input rows could give you any set of output rows. So it's an arbitrary thing. And if your table function is being executed as a leaf, because it didn't have table arguments, it has only like descriptors and literal arguments, then it is executed with a split processor. So like a data processor, this is just going to like consume every split and generate all the rows. And in addition to the split processor, you have to give the split enumerator, which the function will use to like figure out what are the individual splits that can be executed on every worker. So like some sample TBFs that we wrote, these are really simple ones, but they illustrate the API. So the first one is sequence. So sequence takes 3 literal arguments, a start, stop, and a step. And the result of this table is going to be a single big integer column, which has values starting at start, stopping at stop, and is incremented or decremented based on the step value. So there's also a sequence function returning an array which does this, but this is just to illustrate the purposes of the API. So in this case, this function is executing as a leaf because it doesn't have input table arguments. And in order to make this efficient, your split handling will generate splits telling that like start and stop at these boundaries. And so depending on how many splits you want to generate, you can divide the interval between start and stop by the steps and like give individual splits to individual workers. That will generate like that subset of values. And so the result of the sequence table function might not be ordered because of this, because different leaves have produced different parts of the sequence. And if you want to enforce order, you have to order by the result value. Another table function we wrote, this is also very simple. It's called exclude columns. So this is like select star except these columns. And this is like, this operates as an intermediate node. So it has a data processor. It has two inputs. One is the input table. And the second parameter is a descriptor, which tells you which columns it is that the user wants to omit. And so this table function data processor takes the input vector, drops the columns, and returns the input vector minus the columns back to as a result. This basically is very useful if you want to return nearly all columns but a few. There's another popular function that's called query. And query is like a connector function. So in this case, the user wants to run a query. And the query is actually just a literal parameter. It's like the precise query you want to run on a source system. Like what they want to do is stuff like this, like where they want to run a particular SQL query which has, so this is run on Oracle. Oracle has like a model syntax model SQL syntax. And so this can't be executed by Presto. But the user wants to run this in a kind of federated style. And so this TBF allows you to just take a query parameter, which is like the literal query that you're going to run on source system. And it'll run this as a leaf operator and return results to the user. Yeah, so that's all I had. So this is what table function is about. So the API and the implementation are all velox, but since there's so much tie-up in terms of like the statement analysis and planner, we've kind of kept this in the Presto native execution module right now. And depending on how things evolve and how sophisticated this gets, we'll kind of look at putting it in velox or Axiom or wherever that'll be. There are a bunch of people who worked on this. So I want to thank Michael, Shan, Prateek from IBM, Jay from Uber for reviewing all the code, and Timian for RFC discussions. So that's it. Any questions?
Well, look at us finishing 10 minutes early. It's good. I don't have much to say. I don't want to stand in the way of conference party, but thank you. We made it through day one. I hope it was really great. I think we learned a ton and a ton of content. Everything was recorded. I think it's all going to be on YouTube right now because we live streamed it. So feel free to go back and check. We will see you back tomorrow, same time, same place. Reminders again, enter through lobby 14, same place you entered today. If you have a green lanyard, make sure that you drop it off with security on your way out. We'll give you another lanyard tomorrow. And then if you're leaving, make sure you have a Meta employee with you to escort you out. But please stay, have a drink, have snacks, come hang out. That's why we're here, to hang out and chat and connect with each other, all right? So day one in the books. We'll see you tomorrow. Thank you.